Thank you so much, Elwin, and thank you all for being here. Uppsala is perhaps my main home in Sweden, although I don't dare say that in Stockholm. But it is true. I have been here many, many times. I think I first came to Uppsala in the mid-70s. I remember visiting Chuck Kurland, so at BMC, and have been back quite regularly ever since. I guess it's really nice to be here, as you might imagine. I need to learn how to do certain things, but that will be next time. In any case, it's terrific. I need to apologize that my talk is sort of a bit like I gave, but following Ari's example, I was furiously deleting and adding slides during his talk. I must say, Ari, it's been very interesting to see how your talk has developed. If I was a psychologist, you'd be in big trouble, but it's good. Okay, so I also need to thank very much the Nobel Committee for explaining to me that what I've been doing all along has been multi-scale work. I didn't realize this, but they were very good at selecting an area that I guess we had contributed in and calling it multi-scale modeling. We certainly never thought about it as that. Okay, so without any further ado, I'm going to tell you about how the whole field began, the birth of computational structural biology, say something about the future, which will be multi-scale dynamics. I now use the word multi-scale a lot, because I've been told it's a good word, and then some general thoughts. How it began. So it's really useful to stand on the shoulder of giants, especially if you're (1.64 meters. You know, it's just a good idea, but I think it's always a good idea. And I was very lucky because between 1950, maybe 1948, and 1960, there had been amazing work done by real giants. Linus Pauling in the early 50s, Francis Crick with his model of DNA with Watson in 53, John Kendrew, as Arias said, solving the structure of myoglobin in Scientific American in 1961, Max Perutz, who was the force behind both Crick and Kendrew. He was really the hero of structural biology, a wonderful man. David Phillips, who is the only one of this group that doesn't have a Nobel Prize, but he was a very, very strong supporter of computational biology. At this point, I should say that back in the 60s, getting a paper in Scientific American was like 100 times better than Nature. And the reason is that it had colored pictures. It was the only journal that had colored pictures. So these structural pictures, which were drawn by an artist, were actually on the cover of Scientific American in 1961 for myoglobin and in 1966 for lysozyme. I'm not sure if these guys are my heroes, but this is Teller, who invented the hydrogen bomb, or at least is the father of the hydrogen bomb. He is very important in the story because the Monte Carlo simulation method, which is one of the main simulation methods that we use, not all of us, was really invented during the Second World War in the Manhattan Project. Okay, so basically I've told you a little bit about how it all began. I'm now going to become a little bit more focused and personal on sort of where I enter the picture and how this relates to Aria and Schneer-Lifson. So I've called it the birth of computational biology. And for me, a very, very important person was John Kendrew. It was actually great when we did the Nobel Minds television program 2 days ago. They had a guest book, and I paged back, and I saw the signatures of Perutz and Kendrew and Watson and Crick. And it sort of meant an enormous amount. I actually made a picture of that. But so Kendrew got the Nobel Prize in 1962. This was probably this was the first prize, if you like, for what was then called molecular biology. It's sort of interesting that molecular biology in some places is sort of now no longer a cool term. Back then, computational biology was a really bad word. So these things do tend to go backwards and forwards. So Kendrew got the prize, and then in a very public-spirited way, he went out and he gave a television series that was on the air in 1964 on the BBC, and it was called An Introduction to Molecular Biology, The Thread of Life. If you just read through these titles, you'll see that it really hits all the points of a modern class on structural biology, 1D, 3D, proteins, etc. I had arrived in England as a 16-year-old from South Africa in November 1963, 3 days before Kennedy was assassinated, if I remember the day very, very well. And in South Africa at that time, there hadn't been any television. So I was staying with my uncle and aunt, and I was essentially very cold. English winter was very different from South Africa. And I was glued to the television and remember very strongly the Winter Olympic Games, I think were held in Austria, I'm not actually sure anymore, in 1964, and John Kendra's television program, again at the same time. This says 4th of January, 1964. As a result of seeing this program, I got very excited about molecular biology, but I decided to go to university to study physics. The choice was sort of easy. I didn't want to study chemistry because there was too much to learn. And biology is even worse. There's even more to learn. Physics, you sort of hand-waving, a few principles, and you can make up the rest. So it was a fairly easy degree to do, certainly in England where the degrees are very narrow. Alwyn, I'm sure, will agree with me. But if you do physics, you don't do chemistry, you don't do biology. The furthest afield you go is applied mathematics, which essentially is physics. So it was sort of interesting. It was easy. Okay. Then, what Kendra did was he also sent me to Israel in 1967. Now, the reason Kendra sent me to Israel in 1967 was because he didn't want to accept me as a PhD student in Cambridge. But I had friends who were insistent in business school. They said, go back and complain. And eventually, after a couple of periods of complaining, he agreed to accept me a year later. And that left me a year in between, but only on condition that I went to Israel to work with Shneur Lifson, who's shown on the next slide. This is, I guess, how we were maybe 15 years ago, and this is how we were back then. At that time, I got to Israel in October 1967 and immediately fell into Aria's lap as his programmer. Now, I'd never done any programming before, so he threw the IBM Fortran 2 manual at me and said, this is how you program. But actually, we got on really, really well, and he taught me the importance of numerical derivatives and many other things, and I think I was in really good hands, so I actually went out and started to write a computer program that would be used by Ari and Shneur in this piece of work. But before I get there, the key thing about where biology was in 1965, say, was that biomolecules are detailed. They have atoms that are in the same places always. The atoms move, but they're essentially very, very detailed machines. So these are pictures of myoglobin and lysozyme, and we all have lysozyme in our body, and each of your lysozymes, if it were to be crystallized, would look essentially identical to this. And the atom's vibrating, but the precision is maybe 1 angstrom unit. So there's a very high precision machine, and these machines have a function because of their structure. So when Aria was talking about adding function, it's taking a very complicated object. It makes almost any watch seem really simple. I was thinking of what would be a watch, maybe a watch with 1,000 moving parts would start to, they don't have things like that. But perhaps some mechanical objects from the 19th century would have the same sort of physical complexity as one simple protein. Okay, so the paper that I sort of wasn't involved in, but I helped write some of the programs, was written by Aria and Shneur Lifson as part of Aria's thesis. It deals with a very, very important concept, the consistent force field, a philosophical idea that Lifson had. And the basic idea was that you need to be very consistent. You need to be consistent for 2 reasons. If you're consistent, you often have fewer parameters. And if you're consistent, what you do is transferable, i.e. if I've done it on small molecules, I can equally well do it on proteins. And that is shown in the slide here what the consistent force field looks like. This is basically now a standard molecular mechanics force field. The energy is the sum of many, many simple terms: bond lengths, bond angles, periodic energy terms for torsional terms, van der Waals terms, electrostatics. I mean, what is amazing about this is this was actually something that we were using, even a slightly more complicated version, back in 1967, 68. This is basically the function that is still used today. So it's remarkable that although computers are much, much faster, the functions haven't become much more complicated yet. And basically, you can add dates to this, and you find lots of very dead physicists or mathematicians. So this is a dead physicist's energy function, but still one that is used today. Energy function is just half of what you need. Once you have an energy function, you can actually simulate anything. The potential function in physics gives rise to the behavior of everything. So if you had a potential function for the universe, you would in principle be able to predict how it will be every step later. It's not totally deterministic just because of randomness. You don't have to bring quantum mechanics into it, but systems develop in a well-behaved way. Now, how do they develop? So imagine this is a one-dimensional energy function, say a roller coaster. And if you're at the top here, and you do minimization, you just drop down into the first minimum. That's energy minimization. A useful technique because it takes you from any point to a point where everything is in equilibrium. At this point, everything is balanced out, all the forces are zero, the system is stable. Then you can do that in 2 dimensions. In fact, everything we show here generalizes to any number of dimensions. Normal modes are when you have a minimum and you look at the vibrations around the minimum, a bit like a pendulum moving backwards and forwards. That can again is in 2 dimensions. Molecular dynamics, which is a very important method, was first used on proteins by Macromolecules and Karplus in a very important paper in 1977. But there you go downhill, kinetic energy keeps you going. Eventually I just stopped. I got tired of doing PowerPoint animation. And then finally, the Monte Carlo method is just random jumping, and you accept the jump with a probability depending on the energy of where you go to. Again, these have very, very different dates. This is the birth, the Metropolis Monte Carlo method wasn't published until 1955, but Metropolis was born in 1915. Euclid was born in 525 BC. So the methods cover a rather large range of different scales, and some of them Newton and Galileo, etc. Okay, so now we know we have the energy function. Sorry, I shouldn't have done that. We have the methods. We can now, in principle, calculate anything. So what do we start calculating? And clearly here, I want to focus on multi-scale modeling. So how would you explain multi-scale modeling? So there's this very well-known quote by Einstein: everything should be made as simple as you can, but not simpler. It actually turns out that Einstein, there's no evidence that he actually said it. There's a website called Quote Investigator, and apparently this was actually said by the newspaper guy Roger Sessions in 1950, and attributed to Einstein to make it seem a more cool remark. Now, of course, Einstein isn't here, and we can't ask, and I'm not sure if this is true, but it's still a very important saying. In other words, simplify things as much as you can, but not simply. Now, Einstein was talking about simplification for explaining to people, I think, or even explaining to yourself. In computation, it is really important, because if things are not simple, you can't do the calculation. And the obvious analogy is predicting the weather, which is really easy in California, but I think very difficult in Sweden. And in California, the weather forecast can be done without a computer. You just simply say, tomorrow will be the same as today for the foreseeable future. And I actually heard that on the radio. I was shocked. In Sweden, it's much more work to predict the weather, but clearly you might be able to be more accurate in your weather forecast if you didn't mind taking a week to calculate tomorrow's weather, but that wouldn't be very popular, wouldn't be any use. So the model has to be as simple so that you can actually get the calculation done, but not so simple that it's worthless. And I think in certain places in the world, weather models need to be significantly improved. Okay. So another thing that was very important for me is that what got me into proteins, I was working with Arya and Schnell on small molecules, but at the same time, I guess I like to use my hands. And in Israel, an experimentalist, Natan Sharon, who worked on lysozyme, had been sent on paper a printout of the coordinates of lysozyme and of myoglobin. And the purpose was to actually go out and build a Kendrew wire model. This is the actual model that I built, together with Yuval Eshtad, who was a biochemistry student. I built the model, and building a model is a very painful process. I built one of lysozyme and one of myoglobin, but it takes maybe 2 weeks to build a model. At the end, you know the sequence by heart. You know exactly what the side chains look like. In other words, this is the way I learned chemistry, by having to build a model. But also, having built the model, I suddenly realized these are just atoms. Since the Warshall-Lifson consistent force field can be applied to any atoms, it would be very easy to, it would be possible to ask the ladies who very kindly type punch cards for you to take the listing and type the punch cards, a lot of punch cards, for lysozyme and for myoglobin, and then do a calculation. And this then led to, I think, one of the very first papers that was cited second paper that was cited in the Nobel thing, a paper directly with Schnell-Lifson, where we took essentially the same energy function, put the coordinates of myoglobin and lysozyme as they were in the X-ray structure, and relaxed the whole structure. We very quickly realized it's not a big deal, but that the X-ray structures in those days were not low-energy equilibrium structures. They had bad bond lengths and clashed atoms and so on. But this was the first calculation of a protein. Once you could do this, you could do other things on the system as computer time allowed. Then, as Aria described, we worked together on coarse-grained models. In fact, at that time, all the papers ended up having two addresses on them, Weizmann and England, and MRC, because we were moving backwards and forwards. In fact, what had happened was that after my first year in Israel, I had worked with Aria and Schnell, written the paper that I described a bit back, gotten married, and then moved to Cambridge to do my PhD. So the next 4 years, I was actually doing my PhD. I came back to Israel. Aria and I worked together again, and then we went again together back to Cambridge. So there's a real intermeshing of the work. I'm not going to say any more about this. Then Aria has already described his work on catalysis. It's just a cool picture of him. In fact, there's a really great picture of you in the television program. SVT has a really nice picture of Aria. I didn't recognize you at first. I'm kidding. Anyway, so then moving forward, it turned out that the first dynamics of proteins had been done in vacuum. And I had a movie showing this, but I got bored of showing it to people. It's an old movie made in 1979. It's actually on YouTube. Hasn't done that well. Maybe 600 hits. I tell all my friends, go and hit it, please. So help me. Anyway, so the problem is that doing a protein calculation in vacuum is relatively easy. Doing it in water makes it very hard for two reasons. One is the system becomes at least 10 times bigger. Even a very concentrated solution of a protein in water probably has 100 water atoms for every protein atom. So it's a very, even more than that. Okay. So basically, this work was done together with Ruth Sharon in the audience. And we basically showed in a very difficult calculation, it required 200 hours of Cray XMP time, which I think cost the NSF like $300,000 for one calculation. What we did is we showed that if you put the protein in a big box of waters and did the simulation, then in water the protein remained much closer to the X-ray structure than it did in vacuum. And other people's calculations were much greater deviation, even very short simulations, than we'd obtained. This is now essentially how simulations are done. No one does simulations in vacuum anymore. They put proteins into big boxes of water, and as I said, these 200 picoseconds cost $300,000. People are now doing some runs that are maybe 1 million times longer. So computers have become much faster. Here's just a movie, my first movie, which isn't going to come out. Let's forget about it. Oh boy, the resolution is too high. Oh well. I'm going to forget about the movies, I'm sorry. I guess this projector has very high resolution, but it doesn't show movies. Oh God, it looks like, has it crashed? I'm sorry. Yeah. I'll try cutting down the resolution. Is it going to pick up the signal? Okay, good. I'm going to even go lower. As Elwin said, this is a true demonstration of geekdom. I run a Windows virtual machine under my Macintosh. I might have to restart it. I'm really, really sorry. I do have some more movies. I would just forget about them, but okay. Bear with me for a second. Oh, God. No, sorry. The virtual machine has crashed. It boots very quickly. I just like Windows XP. I would do a song and dance right now, but I can do neither. Come on. I guess to me, every second seems like 5 minutes, so. Now you see scientists under stress. Not a pretty sight. Come on. And I have 16 gigabytes and 2 terabytes of solid state in here. It doesn't do very much for me. God, it's going to be okay. You have to believe. This is our vacation pictures from Italy. So you can enjoy these. There's my wife. This is Cinque Terre. I think it is actually working, but come on. Okay, yes, yes, yes. That's to keep the NSA off my computer. Good, 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 good. Oh, shoot. Now I didn't save the talk, but I have it. Oh, go away. Using different versions of Office on the same computer is truly challenging. That's why I do it. You guys can just see the rest of the movie, but let's see if this works. I think we have success. Phew. Finally, something I feel proud of. Okay, so this is a movie made of the alpha helix in water. It was done together with Valerie Daggett in 1989. It was kind of important because I had to give a lecture. Linus Pauling was in the audience, and he had discovered the alpha helix. I thought it would be cool to show him the alpha helix moving in water, but the movie was made, and somehow in making the movie and filming it off the screen, it had been reversed, which meant that all the helix was actually left-handed. If you just take a negative and you turn it upside down. But it was kind of interesting. You can see how this molecule unfolds and refolds. I'm not going to belabor this, but it was a historically important movie made off the screen of a Silicon Graphics 4D, whatever it was, 80, I forget the number now. Terrible. Okay, so we're up to here now, and I'm sorry it's taken so long. What we're currently doing is to work on multi-scale dynamics of huge structures. I should say that almost everything I'm talking about, I've never talked about in the before, because this was not what I thought the important part of my work was. So when I was in Uppsala a year ago, I was talking about how you solve the structure of very large protein structures with new methods. Anyway, so a key thing in solving very large systems and doing their dynamics is to think in terms of both simplified models where you leave the atoms out, but also reduced degrees of freedom, where you basically have all the atoms there, but they all move sometimes as rigid bodies. Like when I move my arm, the key degree of freedom will be pivoting about this, my upper arm. I don't really care how all the atoms inside the billions of atoms are moving. This show is going to show you a movie done with an ex-postdoc, Shuo Hong, and his graduate student, Daniel Silva. It's just a really nice movie. It actually is some joint work that will be coming out in PNAS soon. And this is a kind of dynamics called Markov state dynamics, where you actually basically explore the energy surface, find all the minima, and then connect them up. And here we actually decompose the motion into 1,000 different minima, got the transition rates between them. This is RNA polymerase, the protein that brought Roger Kornberg, to Stockholm in 2006. And what's going to happen here is that this nucleotide, shown here in brown, is going to jump across this helix to get to here. That's sort of the first step in how you take the blue DNA and copy it to RNA. You've got to basically bring the nucleotide you're copying over here, and you're going to see it's going to jump over. This just shows you the sort of reaction happening, something that Arya also did in his vision movie. So now it's jumped over. It's now waiting for the incoming NTP, nucleotide triphosphate, to complete the reaction. Now, the important thing here is we're looking at a very small part of a large calculation, and that was very important just to explain what's going on. But the calculation itself involves something like 500,000 atoms. Okay. Some other work where we actually take a large system, but we simplify it by doing normal modes, if you like what Galileo did with a pendulum, backward and forwards. But a pendulum moves in one dimension. Here we're going to move the ribosome, different models, maybe 500 dimensions or 5,000 dimensions. These could all be handled. I think in this particular case, we've treated the whole ribosome as having something like 500 degrees of freedom, but all the atoms are there. So you'll see, again, a cool movie. This is the, I guess, the 30S and the 16S, and this is where the light blue thing is the tRNA. This is all the atoms, so this is about 200,000 atoms. This is just the one center for each nucleotide and each amino acid. This is about 10,000 spheres. Yet the motion is extremely similar, so you can actually see that global motion depends on overall shape and doesn't necessarily depend on details. This calculation is important, and this motion is super exaggerated. We just made this movie first time shot. But what's important here is you can actually ask, how do distances between very important key groups change during the motion? And since we have all the atoms here, we can really ask some of those questions. So this will be another fun approach. Just to say a little bit about applications to human health, because this was certainly an important part of this, the potential of computational structural biology, I have an example which sort of illustrates some of the difficulties of applied research. I think that governments need to realize that if you make a short-term investment, you get a very small return, just like if you went to the bank and said, keep my 1,000 krona for 1 week and I want 50% return, they'd basically ask you to leave really quickly. But if you said, I want 0.001%, they'd say, sure, we'll take care of your money. So if you invest things for a short time, you get a small return. And here's an example. It involves calculations. There am I. And essentially in the late 70s and early 60s, working together with Cyrus Chosi and Arthur Lesk, who are at MRC, and a group of experimentalists, I developed a computer program that would allow you to model the structure of any antibody from its sequence. Didn't do great, but did okay. So what happened was that when I got to Stanford in 1987, there was a startup company called Protein Design Lab, actually founded by two people who had left Stanford, Lawrence Korn and Carrie Queen. And they wanted in their company to humanize antibodies. Now, this had already been done, unfortunately, off the screen by Greg Winter and colleagues in Cambridge. But let me just explain the problem to you who don't understand the problem. Let's imagine somebody has a certain cancer. Let's imagine in this case they have something wrong with the interleukin-2 receptor. You would like to take that tissue, inject it into another human being, raise antibodies to it, take the antibodies and inject them back into the sick person. Of course, that is incredibly illegal and unethical and would never happen, even in the scariest countries. What you can do is take those cells and inject them into a rabbit or a mouse. My wife thinks that's also very unethical, but we're not going to go there right now. So the trouble is that you now get the antibodies from the mouse. The trouble is those antibodies won't work very well in humans because they are foreign proteins. Humans say, oh, no, I don't want these antibodies. So now the immune system attacks the antibodies that should be helping the immune system attack the cancer cells. So what you need to do is humanize the antibody. You have to go to the antibody structure and say, keep these parts that are doing the recognition of the cancer cells and try to change back as much as possible to be humanized. Now, the way that Greg Winter was doing it, he was keeping these red loops in the structure, the complementary determining regions or hypervariable loops, and using everything else from a human antibody. So this particular case has the key residues that bind the antigen and has everything else humanized. It turns out, though, that the dark blue stuff may not actually fit the light blue stuff, and what you really have to do is change some of the amino acids that provide a good home for the CDRs. Now, this is not rocket science, but it ended up allowing Queen and co-workers to write a very good patent in 1989, protected the technology, showed that this actually works better than the winter method. And if you now fast forward 20 years, humanized antibodies are big business. There are drugs like Herceptin and Avastin, and read the names off yourself. This is now a $20 billion a year industry. And Protein Design Lab has been collecting 5% of that money for a while. The trouble is that the patent was filed in '89, and add 25 years to it, it's about to end. So, which is fun. I wasn't getting anything of that action at all. I ended up helping them defend the patent in the European Patent Court, etc. But it's an example how a scientific idea, which at the time was sort of like old science, could be repurposed, used to help essentially write a patent. The company wanted to be a biotech company. It ends up now just being 7 employers on the part of California that is in Nevada, so they don't pay California sales tax, and they're happily skiing all the year collecting money. But that's going to change. Okay. Finally, looking forward, and I think a really important thing about getting a Nobel Prize is you have to say this is not the best thing I'm going to do. It's very depressing to say that what you did when you were 20 was the best thing you ever did. So you have to say, I now want at least 2 more Nobel Prizes, and I don't think there's any statute of limitation on how many you can get. But right now, I have a very small group, which is kind of fun. We're working on rather different projects. Nia Kallisman, who's now left the lab, is working on mass spec and EM of large complexes. Andreas Skyvitz is working on new methods to compare genome sequences. Jana Gorfman is working on membrane proteins. And Ivan Ufimtsev is actually trying to solve the phase problem ab initio. We might be able to do that. It's kind of fun. He actually worked on DFT quantum calculations, and there you have to find an electron distribution that gives you the lowest energy. So maybe finding an electron density map which gives you the lowest R value will work. It's kind of fun now, this is especially for Elwin and Sherry. We can calculate the R value of a really, really large structure. Say an eighth of a million atoms and 250,000 reflections in 10 milliseconds on a GPU. Okay, so I've told you about that. Now finally, some general thoughts. There's no doubt that this field has been pushed ahead enormously by technology. Basically, everything has changed by 10,000-fold. Price has gone down 10,000-fold, speed has gone up 10,000-fold, capacity has increased 10,000-fold, and the size of the rooms has gone down by 10,000-fold. Basically, had this been a car, a new car would cost $3, go more than 1 million miles an hour, et cetera, et cetera. We've heard this a lot of times in the last week. Okay, family support is really important. There's a picture of my mother who just left Stockholm yesterday and my wife with our granddaughter. And it's really important because scientists essentially are married first to their science and secondly to their wife. And I thought it would be interesting. Ari and I have both been married to the same woman for a very long time. And I think there may be a correlation between getting a Nobel Prize and having a fairly stable home environment. So this needs to be studied carefully, and I don't know whether I really feel like doing the statistics. And as you know, the old saying, behind every successful man there is a surprise wife. Again, this is a very gender-biased. It should be behind every successful person there's a surprise spouse. And I apologize for that. In California, we're very politically correct. Take chances. So I am now a very avid hiker. This is a pass in Torres del Paine in Chile. I'm actually not doing email because there's no reception. I'm just trying to see how much longer I have to go because we were going up and I have a pack on my back and I was getting really tired. So this is also an excuse to get a break. Everyone else was a lot younger. Take chances, but do not be too stupid. And I'm now famous for this. I came to, in fact, we were planning a meeting in Uppsala. We were actually planning a meeting in Sweden in the summer, and I'd hoped the meeting would be on the archipelago where I'd never gone. The meeting ended up being at the BMC in Uppsala. I was so disappointed that I decided to go to the archipelago on the weekend before. This happens to be the weekend before Midsummer's. So I went to Utto, rented a sea kayak. That was the easy part. I'd never actually done sea kayaking, but I had looked at a flash movie on the internet that I actually had to pay for. And it showed me how you sea kayak, and that seemed pretty easy. Anyway, I got a sea kayak, and in about 48 hours, I went from Utto to Ono, along this path, I ended up, this is actually my GPS track, stopping at an island just about there. It's a beautiful, beautiful place. This is just pictures of my private island, my tent, my sleeping bag. If you ever go camping in Sweden in midsummer, take a face mask. Very important. I didn't. Anyway, but that was really stupid because I couldn't right the canoe if it had gone over. The water was very cold. Not a great idea. My advice to the young, which again has been a little bit overused: passionate, persistent, original, and kind and good. I think those things still are the top things on my list. I'd like to just quickly thank my tiring heroes of science. I'm really pleased that Schneur Lifson, who really is the one person behind all this, has received a lot of airtime. He's very featured in the movie that SVT made for us, and that's great. I was very lucky at Cambridge. These guys are all known to you. Bob Diamond was my PhD supervisor. I was his only student, and I'm looking forward to seeing him in Cambridge in June. As I said, Max Perutz for me is the real hero, although probably John Kendrew had more influence over me than any of the others. Mentioned my group, which is significantly smaller than others. I was counting, you have 10 by 10, and I have 10 by 4. In any case, coming from many different countries, I do want to thank the committee, and this is going to seem strange because obviously I want to thank the committee. But the committee did a very brave thing because they decided to award the prize to computers. This work was very much computational chemistry, and this was very unusual. And they did a very, very careful job. In the last week, I've gotten to know them all really, really well, and it's been a great pleasure. But of course, the big winner is our field. I mean, computational biology is a big field, and suddenly it's okay. It's not a bad word anymore. But of course, you can interpret our field in another way. A week after I got the announcement, I was asked to go into the American football field. Sorry, the non-soccer American football field in Stanford. It was a big game against UCLA, and at three-quarter time, I was put on the field with my grandson and my wife, who actually is out of the picture because she's looking at the television instead of looking at the camera. It's okay. And 50,000 people were screaming, "Nobel Prize, Nobel Prize." That is a serious high. Plus, if you look carefully, as Elwin said, my T-shirt actually says Nerd Nation. That was Stanford's gift to me as chief nerd. Now, this morning, it was a very interesting email that I got. The most respectable Israeli morning paper is Haaretz. It's a very respectable paper. It's up there with the New York Times and so on. And it had this article in its Friday edition, which Friday there's like Sunday. Arya Marshall and Michael Levitt seem to be the cutest Nobel Prize winners ever. And one of my colleagues at the Weizmann Institute said, "Now I'm really proud of you." So Arya, fantastic. And I just wanted to thank you all for your attention.